This video will cover the destructive test of an unrestrained light frame wood structure model. This test is the first part of a comparative study that will investigate the behavior of a light frame wood structure model without a roof harness retrofit system. Pictured here is the setup for the displacement test of the unretrofitted roof. At 10 feet by 10 feet plan by 3 feet in height, the structure is a 1/3 scale model of a typical 10 meter by 10 meter by 3 meter high gable roof house. The model roof has been specifically designed to emulate the behavior of the corresponding full-scale structure under similar wind loading conditions. This is achieved by reducing the cross-section of the roof truss and sheathing components, and selecting a smaller nail size for the toenail connections. For this test, withdrawal of the toenailed roof-to-wall connections is isolated as the failure mode. This is accomplished by over-designing the connections at the sheathing to truss interface and providing internal bracing and tie-downs for the walls. This test specifically assesses the displacement behavior of the roof-to-wall connections over a range of wind velocities. The test specimen is placed such that the ridge of the roof is perpendicular to the direction of wind flow. Visible here are the 4 trusses and corresponding roof-to-wall connections along the windward face of the model. As fan speed increases and suction is induced over the roof, displacement will occur at these locations. Wind speed here is measured by the upstream pitot tube mounted at eave height. As roof-to-wall connection withdraw under suction, evidence of 3 distinct stages of failure will be visible. In order, these stages are initial displacement of the roof-to-wall connections indicating net uplift, initial full withdrawal of a single roof-to-wall connection, and lastly, full withdrawal of all roof-to-wall connections. Initial displacement of the windward roof-to-wall connections can be classified as a serviceability failure, allowing for the formation of a gap along the windward eave and allowing potential wind-driven rain to penetrate the building envelope. Full withdrawal of a single roof-to-wall connection is a structural failure, affecting the load distribution between the roof-to-wall connections and accelerating the failure process by shedding load attributed to the failed roof-to-wall connections towards adjacent roof-to-wall connections. Finally, failure culminates with all roof-to-wall connections fully withdrawn from the top plate, at which point the roof is overturned about the leeward wall. The wind velocity is increased to approximately 15 meters per second, seen here, and held constant for 30 seconds. Already, the flexible sheathing can be seen to be deflecting significantly near the windward edge as the flow separates over the structure. While not visible to the naked eye, laser displacement transducers indicate that initial separation of the windward roof-to-wall connections have already occurred. As the wind velocity is increased to 20 meters per second, here, roof-to-wall connection 3, observable at this point, begins to experience noticeable withdrawal. By approximately 22 meters per second, roof-to-wall connection 3 has experienced full withdrawal, and the uplift it was resisting is transferred to roof-to-wall connection 2, causing it to fail shortly thereafter. The tendency for the interior roof-to-wall connections to fail first is a result of the lateral flexibility of the roof. This allocates uplift unequally by tributary area rather than stiff beam action, which would equally distribute the uplift. At approximately 23 meters per second, roof-to-wall connection 1 begins to fail, followed after a brief period by roof-to-wall connection 4. The delay here is caused by friction, as a video recording of the interior reveals that this roof-to-wall connection pinches the windward wall during withdrawal. Finally, at 25 meters per second, failure of all roof-to-wall connections is visible. At this point, the roof would experience overturning about the leeward wall. However, this is prevented with the use of internal cabling to protect the testing environment.